Hello, everyone, and welcome from the top of Mount Pilatus here in the central part of Switzerland. I'm here with GrowBotHub, a team from EPFL Lausanne, working at the IGLUNA testing campaign on their autonomous farming system. So we have here Jonas, Aurélien, Kepler, and Thibaut with us at the mountain, and we have also a few other people joining via Zoom who will be introduced during the Q&A session. So the IGLUNA campaign is an initiative from esa-lab, which is coordinated by Space Innovation here in Switzerland. We provide the system engineering aspect, but the rest of the work is done by the teams. And if you have any questions during this whole session, please feel free to use the YouTube chat to post them. We will do an extended Q&A session after the introduction of the project, where you can see and ask your questions that are related to this. And with that, I would say there's no more to introduce, and we can directly jump to the project show.
Hi, we are P01 GrowBotHub, and we are going to present our project.
During today's presentation, we'll present all the different subsystems and show you how they work.
We are also going to talk about our main challenge, how many students were working there, and the comparison between last year and what we could improve for next year. So this is our system. Our goal is to grow and harvest vegetables in an autonomous and automated way to provide vegetables every day for the astronaut.
We have 6 different subsystems: the growth modules, the automated platform, the shelves, the network and scheduling, the mixing area, and the robotics station.
Our system can work during 6 months.
We are an interdisciplinary team coming from EPFL. All the sections are represented. We have people from computer science, robotics, mechanical engineering, mathematics, life science, and chemical engineering.
So in the aeroponic team, we worked on the aeroponic models. So the principle of this model is to make the plants grow in an aeroponic way. So the aeroponic is only with water that is sprayed on the roots, and there is air in the modules. So here we can see the plants, where we can see the roots, and the water directly goes to the roots, and the water is with nutrients in it. So the roots directly absorb those nutrients, so it's supposed to grow way faster in this way than in classic soil. area. The aeroponic module is composed with LED sensors and the pumping system. So if we open it, you can see the pumping system here. Each nozzle sprays the water with the nutrients directly to the roots. And inside there is sensors. We didn't implement them yet, but there is the pH sensor, the water height sensor, so we can see if we need to add water or not. And the last one is the electroconductivity sensor. Below the system we can see the lights. So here are the lights, that is blue and red LED, and it's used to enlight the aeroponic modules that will be below this one. To do this system, we were a team of 5 people doing the sensors, the construction of the box, studying the aeroponic at home, and yeah, so 5 people were doing this part of the project. A huge improvement compared to last year is that now each aeroponic module is sufficient in itself, like all the captors, the sensors, all the pumping system is inside one box and not outside of the box. So we can easily translate them from one place to another, so that was the huge improvement for this year in this part of the system. For next year, the purpose is to be able to implement correctly the sensors for them to be working, and so we will be able to have a complete independent box finally.
Our system is made of 4 shelves and 2 small shelves for the robotic station. On each shelf we have 4 stairs, and each stairs can handle 300 kilos. On each rail you have electrical connection that enables to connect the trays and to connect to the pumping system, but it's only working when the tray is on the shelf. The automated platform is the link between the robotic arm and the shelves. So we have a system of forks that extend and retract to grab the modules on the shelves. Then it can go up and down and can rotate on itself to be able to take the modules from each side. In this system we have 3 motors. So one that is doing the x-axis and that slides horizontally. Then we have another one to enable the platform to move up and down, and we have one below that is going to do the rotation of this upper plate. And then we have one piston here that is going to enable the retraction and expansion of the platform. During the whole year, 7 students work on the project, either on the automated platform or on the shelves. The interaction that we had is mainly with the aeroponic modules to do the electrical connection, but also with the network to send the information and to be able to move the automated platform. Compared to the system of last year, this system is brand new, and we had previously a rotating carousel, but now it's fixed shelves. The system is working for the moment, and we are trying to make the movements more smooth. Biggest challenge for this year was that we had a problem in the design of the automated platform, and that we needed to design it again with the help of teachers and workshops.
The robotics team were a group of 8 persons who worked on the automation of the gardening routines. Those include the harvesting of the plants, the pollination ideally, and the logistics of the plant. So if we want to move one plant from one growth module to the other, then we will also use robotic action to do that. So the robotics team was working on different control methods. The one implemented this year is iterative LQR with a RRT seed, and this is done to compute a trajectory, based on an optimal approach, and so that we can implement constraints. Let's say we don't want to collide with the structure, we don't want to collide with the automated platform. All those things are taken care of in the path planning by the control. Secondly, we also interface the gripper of the whole with the whole robotic arm, so that we can also grip stuff. This is especially useful because we want to pick plants, we want to pick new items to make manipulations on the plants, like pollination. And finally, we also tried implementing a computer vision module, which has two main purposes. The first purpose is to detect objects such as fruits, flowers, and the second purpose is through stereoscopic vision, the computation of a 3D map, which can then be used to estimate the volume of a plant. This is especially useful if we want to give some feedback to the scheduling center, which computes predictions about the plant state, so that we can kind of have a closed loop on the plant state. The challenges in the whole system are different. So, for example, when we are looking at the computer vision, we are always struggling with the detection of items. So, to overcome this, we wanted to use mainly computer vision based on artificial intelligence. And when we want to have neural nets doing the work for us, there is a main problem, which is the data set. So the biggest challenge for us was to generate a data set which can be used to extract the features we want. So what we have implemented so far is a strawberry detector, especially for the flowers. So it will detect the flowers, estimate the pose, give the position to the robot so that they can go to the flower of the strawberry. This is interesting because this would allow us to pollinate the flower and thus yield better fruits when we're talking about strawberries, and it is a good proof of concept. So we can already show that we can, through the action of neural networks, achieve a position estimation of a flower. The second bigger challenge was interfacing all the systems. So we tried interfacing the gripper. The last prototype we were not able to do that. This year we can close and open the gripper with success, so this is a big success for us. Also, we have been able to interface physically the system with the rest, so this means that the automated platform can bring the growth modules to the robotic station without having too much the need to check if it's in the right position. This is done through the correct calibration and positioning of the whole structure. And also we have the control routines, which were a bigger challenge. So if we look at the system from before, we had a carousel type system with the arm coming from the top with a top view. This means that the control routines that were written for the last prototype were not completely usable for the current prototype, so that we had to rewrite the whole control environment. This was the first challenge and the biggest, probably, together with that of computer vision. And now we have a good basis to build up more complex routines. So the goal of GrowBotHub would be to harvest plants and pollinate them automatically. This is not possible yet with our system, or just in a rudimental form. And this is mostly because we spent a big part of the time developing the new control environment for the system that we are building right now. Now that we have the foundation, the software foundations, be it for computer vision with the proof of concept with the strawberry flowers, be it the control environment for the robotic arm, be it the control interface for the gripper, we can finally start thinking about bigger tasks like harvesting in a more precise way, maybe leaf by leaf, fruit by fruit, or pollinating in a more precise way, which means grabbing an item which can be used to pollinate, going to the predicted location, doing the routine and coming back, and also refilling the growth modules and all those kind of things, which are a bit more advanced, which have not been developed completely in this semester. So finally, just the changes. Yeah, we just saw that we have not anymore a carousel system. We have a table-like structure. The robotic arm is based in a normal sense, not top-down. And this is a major change. We also have the high modularity and the fact that it's interfaced with a storage unit. This is a big change also for the robotic station. This means it is only working on two growth modules, sorry, on the same time, and not on the whole bunch of growth modules.
The goal of this subsystem is to provide the refilling solution for the aeroponic modules and to adapt the concentration of nutrients according to the plant needs. So to do so, we have different tanks that contains different solutions such as water, the fertilizers, and some supplements. It also has some pH regulators in order to keep the pH of the nutritive solution at the right value for optimal plant growth. So we also analyze the plant leaves in order to see if the amount of nutrients contained in it was similar to the commercial plants. And with the results, we will be able to adapt the nutrient concentrations into the nutritive solution. In total, we were 5 persons working on this system. So 2 of us analyzed the plant leaves, and 3 of the rest of the team was responsible to make the system with the pumps and the tanks. The mixing area interacts with 2 other subsystems. So first the robotic station with the robot, because it has to take the refilling pipe here to put it into the aeroponic module, so the second subsystem, and then the solution will flow through and refill the aeroponic modules. And then finally the robot will just take this pipe and put it back here. Compared to last year, we tried to implement the pH regulators. So the idea is to be able to increase or decrease the pH according to the feedback sensors. And also we have the additive nutrients to keep the right amount of nutrients in the nutrient solution. So basically we have more of the refilling tanks, which are all connected with pumps, and then once the solution is ready, it goes through the pipes here, and it is directly linked to the aeroponic modules. So the main challenges of this year were to implement the different sensors, so the pH and EC sensors mainly. We are still working on getting clean feedback from those sensors, and this will be the major point of improvement for next year.
Thank you. So we are now in the control room where we can control remotely our system. The system is on the Pilatus, and from here we can do remote tests on all the subsystems and check that everything is working correctly. The network and scheduling team is in charge of connecting all the subsystems together. We use some Ethernet routers and some Wi-Fi routers in order to connect all the subsystems and communicate between each other. We use Ethernet cables for the robotic station and the automated platform, and Wi-Fi to connect to the growth modules. We have a top-level controller who's in charge of the overall control of the system. It runs on the Raspberry Pi, and there's also a scheduling algorithm that runs on it. What does the scheduling algorithm do? In order to produce new vegetables every day, this algorithm will calculate when to plant a new seed to be able to harvest the vegetables on the right dates. 8 students have been working on the network and scheduling team. The biggest challenge with this team is that it's really highly connected to all other teams, and we need really to work with them. Compared to last year, we've changed the overall system to run on Ethernet and Wi-Fi, and for the future, we'll continue this implementation that works well.
This is our system. So we have the shelves on both sides, we have the robotic station on the left, and we have the automated platform in the middle. Our modules are located on the shelves, and the automated platform is going to grab them and bring it to the robotic station. Under the robotic station, we have the mixing area where we are going to do the solution with the nutrients.
So, to make the whole aeroponic plant to work, we have designed an electronic board that allows to control the pump inside of it to spray the nutrients onto the roots, but also to control the LED here in order to simulate the sunlight. And for this, we have implemented those power stripes that allows to connect this system to the whole main supply. And this allows to control the aeroponic box independent of the position onto the mounts.
Thank you for watching our project show, and I hope you've enjoyed it.
And we want to thank all our sponsors who made this project possible. We especially want to thank Maxan, ITEM, KUKA and EPFL, who gave us a lot of support. We also want to thank all the teachers and all the students who work for this project.
Especially Space Innovation and EPFL Space Center.
Thank you and see you soon, maybe on the moon.
What an exciting video. Thank you so much for preparing this, and I hope you enjoyed it as much as we. Already a lot of questions coming in, and I would suggest we jump right into the Q&A session. Starting with the first question, in what order, in what other environment can your system be used?
So I will answer this question. Our system could be used in places where the access to water is difficult. So, for example, in a desert or where the land is too dry and is not fertile anymore.
Thank you so much, Amelie, for this answer. Next up, what is the advantage of aeroponics compared to normal agriculture?
Thanks for this question. So in normal agriculture, a lot of the water flows just in the earth and it is not used by the plants. But in aeroponic, thanks to our closed loop, all the water that is put in our system stays in the system and can be used by the plants. So that's the first advantage. So we can keep up to 90% of water in comparison with traditional agriculture. The second advantage is that we have all the parameters in the hands. So like we can monitor all the pH and all the elements in the nutritive solution. So that's the environment is optimal for the plants. So the plants can grow then faster in aeroponic or hydroponic than in the traditional agriculture.
That's very exciting. Thank you, Thibaut, for answering this one. Now coming to the next question, it's about the commercialization of your product. Do you plan to make a business out of it?
So thank you for this question. Actually, we thought about it. For now, we want to stay a student project to be able to develop the prototype as much as we can. But if some of the modules, for example, the harvesting and pollination modules is going to be better in the future, maybe can just go out of the association and be commercialized on its own.
That's amazing. Thank you so much for this answer. Now, coming towards the next steps of your project, what is like the most innovative part of this system, and how are you planning to develop it further?
So the interesting part about our project is the full automation of the harvesting and pollination routines, so the gardening routines of the whole GrowBotHub system. We are aiming to close the plant's life cycle in order not only to harvest and have food, but also also to sustain the food production. That means we need to plant new plants once the food has been harvested. So in order to do that, we need to pollinate flowers to create the seed and then seed them, and new plants can grow to grow other food. So this is the part which is most innovative, and yeah, we're working on this at this stage. We are working on the basic control routines to do that, and in the coming semester we will probably be implementing the more advanced routines to do so.
Thank you, Jonas. Building up on this question, what we have been now here for almost 10 days now at the testing campaign. Also prior, you did some preliminary tests. What are your results so far?
So thanks for the question. Essentially, during the field campaign, we've done a lot of the testing because of COVID, and also the fact that our system is so big, we can't actually do a lot of tests. And so now it's really our moment to build it and see what works and what doesn't. So we're kind of really building up what we already have. And I'd say that all of our modules are about 65%, operational capacity. So we're on good track, but we're not really quite there where we wanted to be yet.
Thank you, Kepler. The next up is, you already talked about the most innovative part of your system, but what's the biggest pride you have with relation to this project, I'm guessing?
Yeah, I'm going to answer this question. And basically for us, one of our greatest pride is that we've been able to reach our goals and to build actually the whole system, even with all the COVID restrictions that we had this last years. And also because of its impact on the delivery dates of the different parts. Another thing is that we haven't been able to actually meet all together physically until now. So it was quite a challenge to organize the whole event and work on all the subsystems independently and still be able to make it run.
Thank you for this great answer, Antoine. Next up is, at what stage is the autonomy of your system already?
I can take this one. So right now, we're testing, as Kepler said, all the subsystems individually. The basic robotic routines works. The growing of the vegetable works, but the autonomy is just not there yet. But we hope to finish the last part that we wanted. So finish the control of the automated platform to try to have 1 day of autonomy during this campaign.
That's an amazing goal. Thank you very much, Aurélien, for answering this question. Next up is, can you explain the scheduling algorithm of your system a little bit more in detail?
Absolutely. So essentially, because our system wants to be autonomous, we need it to be run essentially entirely by the computer. And so what we can do is give the computer inputs and say, okay, for instance, I want, like on day 10, I want a certain number of, fruits or whatever. And then the computer has to be able to propagate that into the past and say, okay, well, that means that I need to plant this seed at this time, and that it needs to be in these conditions, during these periods. And so that is the entirety of our scheduling system, which kind of decides based on what we want, what the robot actually has to do to achieve results.
Thank you, Kepler. Next up, the whole IGLUNA campaign is a highly interdisciplinary project, but especially your system even combines robotics, some system engineering, software engineering, also biology experiments. So what did you find is the biggest challenges related to this interdisciplinarity?
Yes, and as my colleague said first, COVID plus high level of interdisciplinary is really challenging. We all have to work together, and people at EPFL have different culture depending on their sections. So people in robotics and people in computer science don't think the same way. People in chemical engineering and people on mechanical engineering don't think the same way and don't communicate the same way. So being able to share all the knowledge and to coordinate all of this has been a real challenge, but also a real opportunity for us to learn how the other works and how to collaborate with them for the future and for all our future career.
Amazing. And I saw also during this whole campaign that you managed very well, starting at the communication side, but also bringing the systems together in the end on a technical level. So congratulations also on that one. That's really impressive what you pulled off during this year and the rest of the past years even. So you were first talking about the remote control aspect of your system. You bring together several aspects, but the aim of this remote control for your system in general?
So the remote control is essentially, because our system aims to be fully autonomous, we only really have it as a supervisory capacity. So we need to be able to monitor what is going on just to know if there's some sort of error that the system didn't catch. And we can also issue commands if there's something extra that needs to be done. But it's mostly really just there to observe what's going on and also alert the astronauts if some food is ready, for instance.
Thank you, Kepler. You said if some fruit is ready, for instance, can you harvest fruits on their own?
So we can. Right now, it's a rudimental form of harvesting, which relies mostly on human actions also. So we just take the plant, we put it in a separate container. Once the scheduling algorithm tells the whole system, okay, a fruit is ready now or a vegetable is ready now. And this is clearly rudimental and not really autonomous at all. If we think about it, the human has to do, a person rather, has to do most of the work, picking the berries, for example, if it's a plant of strawberries. And what we want to achieve in the coming semester is a more autonomous way of harvesting, which implements computer vision systems to be able to identify objects such as fruits or vegetables, and also to be able to then grab them with the robotic arm, go specifically pick strawberries. That would be like the ideal setup for the system, but this is the goal we want to work towards right now, but it's not reality yet.
Fascinating goals you've set yourself there, really exciting. Now coming over to the human aspect of it. Food needs to be healthy. Food needs to be not contagious. How do you deal with radiation during your phase of system deployment and the process of running it?
I can take this one. Thanks to IGLUNA, we have a wonderful habitat, and for our project needs to be run into a habitat or into a controlled environment where temperature, humidity, and protection against radiation needs to be performed. So our system do not implement this, but rely on other teams and other technologies. During this this event, we met the habitat team, who've made an amazing work. And I'm sure that in the future, protection against radiation is part of their goals. And for future collaboration, we can just all work together, and each team's making what they do the best. We're making vegetables, they're making habitats.
Thank you, Aurélien. Great to hear that you are also collaborating with the other projects here. That's the kind of interdisciplinary communication we want to train here, and we want to master during this campaign. The next thing is you were already explaining the benefits of your aeroponics modules. Which LEDs are you using to make sure that the plants are growing in the best manner?
So we are using LED, which are designed to grow plants. So like the spectre of the light is designed just for the plants. So it's sufficient, and it's already a lot used in the agriculture. So it's not something new. We know how to do that.
Super. Technology development is always about taking stuff that works and using it, and only improving the things that don't work yet. So great learning also here. Next up is your system really scalable for bigger applications?
So right now, right now we're having a few issues, but there are structural issues with the design that we have. But we did design this entirely with scalability in mind. So with only a few robotic arms, we should be able to serve quite a number of growth modules and shelves, meaning that this system should be extremely scalable on a bigger lunar base than just a few astronauts.
Thank you, Kepler. I can imagine bringing up a large system to the moon is a challenge. And we have some viewer asking, how are you planning to bring it actually up to the moon, assemble it, dismantle it? Would this be astronauts doing it, or would it also assemble itself?
Maybe I can answer this question. Yes. Right now, this year we've done a proof of concept for the whole system. But as you may know, aeroponics mix low tech and high tech, and most of the parts could be produced on the moon. With the future of the project, we really want to integrate this process of building most of the parts for and on the moon or on extreme environments with the stuff that we have there. And that will reduce the amount of material that we need to bring. The future design will mostly incorporate this. So that's one part of the question. So right now, yes, we need to bring it, assemble it, and disassemble it like that. But if the proof of concept is working, we'll just go one step further and try to use recycled material from the moon.
Thank you very much for this elaborate answer. We have now a comment from Sasha to Kepler. Could I please steal your T-shirt? He's super happy about that. That's really cool. Nice T-shirt, by the way. Oh, that's very kind of you. Maybe summing up or already going towards the last questions. How is your support looking currently? Are you still looking to be supported from a university, from industry? And also, what's the next steps towards having a lunar mission for you guys?
Maybe someone will take online. Okay, I can take it. Right now, as a student project, we are really lucky to have great support from our university. So we're working with amazing labs that helps us a lot for developing the project. So we work with maybe 8 or 9 labs at EPFL. We have amazing support from the school in financing the project. We work with our sponsors that helps us a lot, but obviously to go further, we'll need some support. And as like all projects, we need foundings and we need help. And that's up to the next team and the next board to continue developing a partnership with industry and university.
Thank you, Aurélien, and thank you so much for joining in. That was the last question of today. Thanks for actively participating in this session. I hope you liked the answers of the team. I think they were very encompassing and very detailed. So great work by you. Thanks, Thibaut, Kepler, Aurélien, and Jonas. And also thanks, Amélie and Antion, for joining in from virtually. And yes, with that, we're looking forward to the final days of IGLUNA. Hope that everything is working for your system. And we're super excited to seeing the results in the end. So thanks again for joining in and have a nice afternoon.
Thanks, Daniel, for